In this video, I'm going to walk you through Desmos' new feature, the logarithmic axes. If you're new here, I'm a certified math and physics teacher in Ontario who holds a master's degree in statistics. So before we get started, I think it might be useful to review what logarithms are and how they're important when it comes to graphing in Desmos. So let's say we have an exponential function, a to the x is equal to y. That's a function that the base is a constant a, x is the variable, so it's an exponential function, and it looks something like this, right? Horizontal asymptote and so on. But we can rearrange this, so we can solve for x, that's another way of saying it, isolate x, by x is the answer, log base a of y. That's another way of saying this. We're taking the log base a of both sides, and then that's going to give us x, because log base a of a is just 1. You can drop down the x, and then log base a of y. So if we have an example of that, that would be, let's say we have 2 to the x is equal to 5. Well, the 2 to the what is equal to 5? Well, 2 to the 2 is equal to 4, and 2 to the 3 is equal to 9. So we know it's going to be a number between 2 and 3, and it's probably going to be something closer to 2 than closer to 3. So when we use this in our calculator, and if we use the formula, that means that x, we take the log base 2 of both sides, so that would be log base 2 of 5. And you can plug that directly in your calculator, or you can also use the change of base formula if you don't have the base thing, and then that's going to work. So it's going to be log of 5, and by the way, that's base 10 when there's nothing, and log of 2. So if you put that in, you're going to get 2 point something. I'm not going to do it here. So 2 point something, and then 2 to the 2 point something, that's going to be equal to 5. You can test that out in your calculator. So you put the answer in here, and that's another way of saying we're just solving for x, right? So now let's hop into Desmos and see how that relates to the new feature they just added. The new feature they added, you just need to click on the wrench, and then they hit it here. So more options. We have the linear axes, so that's what we have. Every jump is a jump of 1 by default, and the grid is there's 5 spaces, so that would be 0.2. But then when we change the y-axis, for example, well, we see that the jumps are not 1 anymore. They're jumps of 10. And they're not linear jumps of 10, because then the next jump is 100. So every time it's a geometric sequence, right? So it's times 10 every time. So 0.1 times 10 times 10 times 10 times 10, all the way to very, very big numbers. And you're not going to write the big numbers. We're just going to write the scientific notation, which is 10 times 10 times 10 times 10, 12 times. It makes sense because we have 12 jumps in this space here. And the other thing I want you to notice is if we go back to our home screen, we can click on the house. The sub grid lines, the minor grid lines, are not evenly spaced as well. So the first thing we're going to figure out is what those subgrid lines mean. So I'm just going to create a folder here, and I'm going to call it grid. And what we're going to do is, let's say we just look at the 1 here. We're going to create a little slider. So when we want it to start at 1, between 1 and 10, right? And you see that it slows down. What's going on there? Why does it slow down and speed up? Well, the distance between each grid line is a tenth, or it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you divide the distance between 1 and 10 in the units. So this distance reduces as we move closer to 10. Okay, so the subgrid lines are not linear anymore. That's the first thing we want to find out. The other thing is, why do we care? Why is it useful to have log axes? So I'm going to create a folder, and I'm just going to delete this one completely. So let's call it data, And let's create some artificial data. So I'm going to create a list, just 1, 2, all the way to 30. So that's going to give me 30 x values, 1, 2, 3, all the way to 30. And you can put those in a table, right? You just type table. Instead of x1, we're just going to put our list. So here's my 30 data points. And then we're going to put some y values, which would be 10 to the x. So 10 to the 1 is 10, 10 to the 2 is 100, and so on. So let's just write them here. So then 1 to the 10, or 10 to the 1 is 10, 10 to the 2 is 100, all the way. And then we're going to get 10 to the 30, which is pretty massive. So at the bottom left here, you have zoom fit. That zooms on your data. So let's put the linear axes on both of them, like we're used to. And let's zoom fit this thing. Oh, that's an awesome graph, right? Because we have one very, very, very big value and then another very big value. And all the other ones are still big, but nothing close compared to this. So the x-axis seems fine. The distance is equal, but the y-axis, the distance is not even close to being equal. So how would we plot this in a reasonable manner? Well, keep in mind this is a linear axis, the y-axis, so let's change it to the logarithmic version. And voila, we have a nice straight line on the logarithmic scale. So try to think why a logarithmic function or exponential function looks like a line on a logarithmic scale. So that's going to be your homework. And finally, just for fun, I encourage you to turn both axes into the log scales, and then try to plot some functions and try to predict what they're going to look like beforehand. So let's go back to the home base, and then we go y is equal to x. What does that look like? And that looks exactly like a line. What about if we do y is equal to x squared? So I encourage you to pause the video here and try to predict that in advance. So y is equal to x squared. That's still a line, but the slope is different. So try to figure that one out. And then you could do y is equal to a to the x. Or let's put a number instead of a, so 4. Oh, that still looks like this. Why is that? Try to figure that out. You can even do some funkier things like sine of x. Oof, that looks very, very special. So try to figure those out and try to predict them beforehand. That's the hard part, and it honestly challenges your understanding of exponential functions even when you have a pretty strong grasp on them.